Today we'll talk about Ohm's law and how it applies to series circuits. To understand Ohm's law, we need to understand three important variables. Voltage, which is the electrical potential difference between the high and low concentration of electrons. We measure this in volts. The voltage is the pressure. It's what pushes the electrons, it's what pushes the charge through the circuit or out of the power source. The current is the physical flow of electrons. We measure this in amps or ampere. Resistance. This reduces the flow of electrons. Any electrical device has resistance. Even wire has resistance. We think of this as the friction. This is what slows down the flow of electrons. We measure our resistance in ohms, or the omega symbol. Voltage is equal to the product of the total current and the total resistance of a circuit. This is how we define Ohm's law. More simply put, it's a formula. V, which is measured in volts or voltage, equals I, which is our current measured in amps, times R, which is our resistance measured in ohm. This formula is at the basis of our circuitry understanding. So let's look at an example here. If we have just a basic circuit, so we have one resistor, it makes a full path from the battery cell. Make sure that at each location, each resistor, each motor, each bulb, each anything, we have V, I, and R whenever you draw your schematics. So we have total voltage, total current, and total resistance at the battery itself. Let's say we have a 1.5 volt battery and a 100 ohm resistor. In order to find a third piece of information, we need to have at least two of our givens. We need to either have two of voltage, current, or resistance in order to find the third. Since this is a very basic circuit, I know that the total resistance has to be 100 ohms, because that's all the resistance I have. I know the voltage has to be 1.5 volts because we only have one single basic circuit. I'm going to substitute into Ohm's law formula in order to find the missing information. So I'm going to take V equals I times R. Beyond basic circuits, we have a couple other layouts like series circuit. A series circuit, the electrons and the charge travel from the battery or cell through all of the resistors in a row. They pass through every single one. So we can see this designed like so. In this case, we have three bulbs in a row hooked up to a battery. We have a switch in this case that controls whether the current flows or not. That switch decides whether we have a broken circuit or a full circuit. We have another diagram here, more simply put, more schematic looking. Notice the current has only one path. It has to follow through all of the bulbs. From one end of the battery, through all three bulbs, back to the other end of the battery. That's the path that the full circuit has to take. And here are two more final examples. Notice that in all of our examples, we see one battery or one cell in this case going through one continuous path through all of our resistors. When we talk about resistance in a series, it's helpful to look at it as a toll booth. One single resistor can be viewed as a toll booth. That whole current has to pass through one resistance causing toll booth. So it slows things down. It causes, for lack of a better word, it causes friction. It rubs against all of those charges, all those electrons. It slows them down. So we have one single resistor in this example. Here we have three in a row. They're placed in series. They're right ahead of each other. When I add toll booths, it slows down traffic. The more resistance, the more traffic. The amount of traffic is the same through all resistors. So if we go in with a certain amount of electrons, we're going to come out with a certain amount of electrons. They're just squished through that resistance, through those resistor toll booths. So it's a constant current in a series. These tendencies can be summed up like so. Our total resistance is equal to the sum of all the resistors. So if you have 3 resistors, add them up, that's your total resistance. If you have a current, it's always the same. Once I know the current at one point throughout my circuit, my series circuit, I end up with my current at all points. So at all resistors, at all bulbs, at all motors, at all buzzers, and at the cell, the battery itself. The power supply, or the voltage at the power supply, which is the total voltage, is equal to the sum of the voltage drop, so the change in potential energy between 2 points on the circuit. Using Ohm's law, we'll be able to find each of those individual voltage drops at each of our resistors. Add them up to get the total voltage, or the total power supply. We have an example here. I'm going to start by calculating my resistance. I was given my resistors, all 3 of them. Add them up. 6 plus 4 plus 14 gives me a total of 24 ohms. That's my total resistance. Calculate the total current. To do that, I need to use Ohm's law. I know my total voltage is 12. I know my total resistance is 24, so I just need to solve. 12 divided by 24 gives me 0.5 amps. I'm going to write that right in. Notice I have V, I, and R for each one of my resistors, bulbs, etc., and the cell itself. Now I need to apply my tendencies. With a series circuit, I know that the current is the same throughout. So I can take all the same, I can add up all my resistors, which I already did. The current needs to be the same, and then the voltage, I add up all of my voltage drops. The only one that I can really apply of these tendencies right now is the fact that the current is the same throughout. However, that sets me up with 2 of my 3 givens for each of my resistors. That means I can find my voltage drop for each of those. So I can go through and I can use Ohm's law, V equals I times R. 0.5 times 6 gives me 3 volts. 0.5 times 4 gives me 2 volts. 0.5 times 14 gives me 7 volts. Not only was I able to find each of those voltages, but if I add them up, 3 plus 2 is 5, 5 plus 7 is 12, I get my total voltage. Each of the individual voltage drops adds up to the total voltage of the circuit in a series circuit.